All right. Apologize. Just forgot to hit start on the record button. So for those of you watching on YouTube, we're just going through simple facts of vector calculus, and we're talking about gradients. So this gradient operator is it's built out of a unit vector multiplied by the corresponding partial derivative. And we think of it as acting to the right. So in particular, I can think about this gradient as acting on something, maybe a function, a scalar function. And then I think of it, I just write it down. And the way I kind of imagine is I'm feeding the function to the gradient operator. So, but really you just distribute and you apply the partial derivatives to each to the function. Okay, so it would, when applied to a function, it would give me the x unit vector times the partial with respect to x plus the y unit vector times the partial with respect to y. Okay. All right. So is that familiar to everyone? You remember doing that? Okay. Now, so this thing, what is it? Well, it's a vector, right? It's x hat times some number plus y hat times some number. Now, I don't, you have to know what the function is to tell what exactly that vector is, but it's a vector. Fine. And that means you can do other things with it. You can take, dot products. You can take cross products. You can do lots of things. Looking at our formula for a small change in a function and using this vector displacement that we defined, we can use the dot product to say that basically the change in the function can be written as the gradient of the function dotted with the displacement vector. Okay. How is that? Is that okay? Is this different than how it was presented in Calc 3 or more or less the same?
I'm fairly certain it's different.
Okay. Some people are saying different. Okay. Well, I'm trying to do it in one day. They're probably trying to do more. Okay. You know what? Let's switch and why don't we do some practice? Okay. So I have some functions here, and what I want you to do is to work out for these two functions, f and w, work out the partial derivatives, work them all out, and then write down the gradient vector evaluated at x, y, maybe z. All right. How many people have partial derivatives for f of x? Do we have those? Some people do. Actually, let me stop. Is anyone stuck? That's kind of the first question. Nobody feels stuck? All right. Well, let's kind of work through this. For f, I would want to work out partial with respect to x on f. So all I do is just pretend that y and z are constants. So I just go through it. So that's going to give me 12x squared y squared. If y and z are constant, this whole thing is constant, so I ignore that. Z is a constant, but I still have x there, so I get plus, oh, it's going to give me minus, I'm going to have z cubed, I'm going to have x cubed, and I'm going to have a minus 2 there. Y I take as a constant, and then I get x there, so I get minus 16 x to the 15th. Does that match what you guys had? Okay, I can do partial y acting on f, and I get 8x cubed y minus 4e to the z y cubed, because again z is constant for the purposes of taking a partial derivative with respect to y. I get a 4 out front and I lower the power, and then this acts like a constant, so I don't worry about that, and I get plus 4. How does that compare? Does anyone have anything different? Michael's nodding yes. Partial z. First term acts like a constant. Second term acts like minus. The derivative of e to the z is e to the z. Y to the 4th. And then I get plus 3z squared over x squared, constant, constant. How did we do so far? Yeah? All right, so then if I wanted to work out the gradient on f, it would be this is what you can do when you're the instructor. And I would say it's heart times x hat plus square times y hat plus triangle times z hat. I'm not going to rewrite all that crap. Okay. How was that? Was that super hard or pretty straightforward? You got it. Okay. All right. Okay. Let's work out. Let's do the next one. Okay. So let's work out all the partial derivatives on w of x, y, and z, and then write down the gradient. Take a second and work that out. Isaac, we're just practicing taking partial derivatives. Is that something you've done before?
Yeah.
Okay. Give me a thumbs up when you guys think you're done. Let let me rephrase that. When you've completed. I mean, some of you guys felt like you were done before we even started. Okay, another minute or two, and then I'll kind of start in. Okay, so let me start in here. So for number 2, I'm working this out, and I wanted to work out the partial of w with respect to x. So now I'm holding y and z constant, so this first bit doesn't matter. Sorry, y and z constant, so the first bit does matter. So I'm going to have the chain rule here. So first you take the derivative of the outer, and then you work your way towards the inner most function. So this is going to give me derivative of cosine is what? Do we all remember that?
Sine.
Careful.
Negative sign.
Negative. If it has a co in it, then when you take its derivative, you're going to get a minus sign. All right. So this is going to give me minus sine of x squared plus 2y. That's the derivative of kind of the outermost function. And then I have to take the derivative. I have to multiply it by the partial derivative of the inside, which in this case would be just the partial with respect to x. So that's going to be 2x. And then I have to do the same thing here. So there's an x up here. So that's going to give me, it's going to be minus. So it's going to be the partial of the whole thing of this term. And it's an exponential, so I get an exponential back. And that's to multiply by the partial derivative of this inner thing, sorry, which is just with respect to x is just going to be 4. And then this bit doesn't matter. Questions on that? Can you give me a thumbs up if you were able to get that part? If you didn't get it, was it did you forget the chain rule? That's usually, okay, everybody says they got it. All right.
Sean, does it matter which order? Like I had 2x in front. Do you really care now? Okay.
Multiplication is commutative. So.
Yeah, I just didn't know if you had a preference when you're looking at it.
No, just usually I do it like this. Well, to be honest, if I was doing it myself, I'd pop it over. But when I teach it, I write it like this. So I can say, like, if I have f of g of x, then I can kind of say it looks like fractions. df dg, that'd be the first bit, times dg dx. So it looks like fractions. So when I teach it, that's how I do it. If I'm doing it myself, I flip it around. Sorry. 100 clicks to get rid of anything. All right. Now we can work out partial y. Okay, so I get the first bit, so that's going to give me the same minus sine of x squared plus 2y. And now the partial derivative of the interior function is just a factor of 2. And then I do the same thing up here. And I get minus e to the 4x minus z to the 4th y. That's the outer function, times the partial derivative of the inner function. And I'm taking a partial with respect to y, so x and z are constants, and so I just get a factor of minus z to the 4th. And then I pick up something from the last term. So that gives me a plus 3y squared. How'd that go? Can you give me a thumbs up if that's what you got? Yeah, okay. And I will just tell you, the type of functions we get in this class aren't this complicated. I'm not saying you couldn't do an electricity and magnetism problem where this came up, but that's not the kind of example we would be doing. Ours are they're just simpler shapes and things. All right. Does anybody need me to do the next one? I think it's easy. It's only one term. Okay, I'll do it. Partial z. First one goes away, last one goes away. I only get something in the middle, and that's going to give me, so I'm going to get a minus, and I get another minus. You're just going to end up with an overall plus sign, and I'm going to get 4yz cubed e to the 4x minus z to the 4th y. I think that's right. Is that what everyone has? Just kind of simplifying it all in one go. Awesome. So you guys are officially experts at partial derivatives, because if you can do that, you can do anything. It's just more of the same. It's not harder. It might be bigger, but it's not harder. Okay, let's go back to what we were doing before. All right, so we were talking about partial derivatives. We put them together to form a gradient using unit vectors. What does that mean? Well, this is a useful fact that we will use, especially when we get to electric potential and voltage. So if you imagine you had some curve, so this will be a function of 2 dimensions, a function of x and y. All right. We already said that you could write a small change in the function as the function at a point plus how much it varies. And that would give you the total change in the function, or the new value of the function. Okay. Now, let's kind of imagine a special curve or special variation. And we want to consider variations which don't change the value of the function. So these are called level curves. So you could imagine, so the pink curve is the actual height for any x and y. And then imagine you were at a point and you were to walk over to here. Okay, so that would be some change in x and some change in y. So you would have, so it would be, you'd start here, go to here. And if I were to draw that in the xy plane, that would be delta r. And because these are on a level curve, I would label it level. Just so I know that, basically, so I know I'm walking level. I'm not walking up the hill or anywhere else. I'm walking along a slice. All right. So I could just put subscripts everywhere just to indicate that. Okay. Now, by definition, how much does the function change as I walk from first point to second point? along a level curve. How much is it changing?
Zero.
It's not. Yeah, that's right. So it's not changing at all, which means, and somehow I didn't write this. Oh, so when you write out, you start at some point, you shift it over by a level displacement to a new value. These have to be the same. Okay, these are the same. Therefore, this piece must be 0. How do we feel about that? Is that too big of a jump, or does it seem okay? Billy said he's kind of not sure, it looks like. So the idea, Billy, is before we wrote out the formula, as you walk around in the XY plane, we wrote down the formula for an arbitrary path. If we specialize that formula to the special case where you're on a path where the initial and final heights are the same, then that means that these two terms have to be equal to each other. Consequently, along a level path or on a level curve, this bit must be 0. Okay. So, all right. So that means that if you take the dot product of the displacement along a level path or level curve and the gradient, you get 0. They're perpendicular. Okay. So we see that this vector, this combination, is perpendicular to a level curve. So the gradient is perpendicular to the curves where it's not changing, which kind of by linearity, and yeah, it kind of, there's a little bit of thought that has to go into it, but you can convince yourself pretty easily, I think, that means, therefore, if it's perpendicular to the direction where it's not changing, it actually points in the direction where it is changing. And in fact, changing the most. So therefore, a gradient points in the direction of steepest descent. Okay. So, yeah, I don't know, that's just one of these things you got to know. I'll go ahead and give you a precursor, since I can tell you where we're going with this. It turns out that there's something called an electric field. Okay. We're going to talk a lot about this all semester. So don't worry if it's overwhelming. Don't worry about it. It turns out the electric field, as long as things are static, equals minus the gradient on the electric potential, but you can think of it as voltage. So you can imagine as you move around in the world, there's a different value of voltage that you can measure. The electric field is going to be related to minus the gradient of it. What do you know about voltages in a wire, in a metal? What did Tim teach in circuits? How much? What's the voltage drop in a wire?
0.
0. That means voltage is constant in a wire. That means a piece of metal, or any piece of metal. That means any piece of metal is a level curve of voltage because it's not changing. Therefore, the electric field is always going to be perpendicular to a piece of metal, like right, like along the edge of the metal. like along the edge of the border of the metal. In fact, sorry, not perpendicular. I'm getting ahead of myself. Well, take that back. I'm trying to give too many examples. Voltage is constant. I'm saying that not correct. What I should have said was, if the voltage is constant in the metal, the gradient, which is a derivative thing, is going to give 0. So the electric field is 0 in the metal. Sorry, getting ahead of myself. Vanishes inside conductors. Sorry. I don't want to get into the gradient part and how to interpret that quite yet. All right. So, so that's kind of an interesting thing. Who remembers doing this stuff from Calc 3? The gradients were perpendicular to the level curves. Yeah, probably did it when you were doing Lagrange multipliers a little bit. Yep. Okay. Good. All right. What about a divergence? Did you guys talk about divergences in Calc 3? Okay. So the gradient is a vector thing, and we let it act on a function because it makes sense. Really, we can take derivatives of pretty much anything, but like partial derivatives of anything, but it makes sense to multiply a vector and a scalar. So that's kind of a sensible thing to combination. Other sensible combinations, basically every way that we had to multiply vectors gives us a sensible object we can define. So the sensible ways that we can multiply vectors are dot products and cross products. And so using the gradient operator and a dot product or cross product, we can form some sort of other generalized vector derivative. And those are the things that we're allowed to do. So using a dot product, we call it a divergence. Okay, I should have written it out what that actually does. So let's just think about that. So this would be like partial x hat. Remember, x hat's a constant, so that it doesn't matter whether I write it first or write it second. It doesn't really matter. Maybe, let's just be consistent. It doesn't matter too much. So I can write that as x hat times partial derivative with respect to x plus y hat times partial y dot v x hat plus v y hat. Right? Just writing out random arbitrary vector. We're assuming everything's, varying. It's not constant. Now, the partial derivatives don't care about the unit vectors here because I'm in Cartesian coordinates. So really, I could just do a simple dot product. And what that does is, remember, when you take a dot product, you just pair up the x pieces and then pair up the y pieces and then add the results. So when I pair up the x pieces, it's going to give me a derivative on Vx. And I'm going to get a pickup in the y direction. I have a derivative on Vy in the y direction. And I'm going to get the partial of x acting on the x component plus the partial with respect to y acting on the y component. So that's what it would evaluate. And if you had 3D, you would just add one more term. It just grows. Okay. So notice after taking the dot product, there are no vectors anymore. So what you're left with is some scalar quantity. Yeah, it's built out of pieces of a vector, but there's no vector left over. It's just a scalar. What does it tell you? Who did you have? Stephanie? Aaron? Stephanie. What does Stephanie tell you? What does a divergence measure or tell you?
Isn't it something with like how far something skewed off from where it was originally? Like it's going away from something?
That's more like, that's just the gradient. That's more like just this by itself, I would say. What the divergence measures, it measures rates of change that are radially oriented. Okay, so this kind of profile, or this kind of profile, is going to have typically a gradient that's not zero. Or sorry, not gradient, a divergence which is not zero. So a divergence measures, in quotes, a flow out or a flow in. Okay, that's what a divergence measures. So this one would have a positive divergence. It's like a source for flow. And this one looks like a drain. So it would be a negative divergence. Right? That's what it measures. Okay. So, okay. So that was a dot product. The other way we had to multiply vectors was a cross product. So that's going to be the other way. So we're going to use a cross product to define a vector. That one I actually did write out. So it's called the curl, and it's the gradient cross the vector field. And I just worked it out for you. So, I mean, you can go through it. You work it out just like you did with the divergence, but do a cross product instead of dot product. So it ends up in the x direction, I'm just doing the cross product. You're going to get partial y acting on z minus partial z acting on y. And the y, and you get a minus sign, and then you get a y hat, and then it's going to be partial x on z minus partial z on x, and then whatever. You just do the determinant, and that's where that comes from. Okay. You guys probably saw these things, especially when you were doing some of the Green's theorems. You would have had some things which kind of look like this, little partial derivatives of things minus other things at the end of the course. I don't know if people remember that. Okay. So divergences measure flows outwards. Curls measure whirlpools, spirals, or like the swirl part of a vector field. So yeah, so that's how that goes. So I don't know how familiar you are with electricity and magnetism from high school. When you have point charges, we will have electric fields, a point charge which is at rest. We will get electric fields which kind of look like this. So shouldn't be any surprise that the divergence of E is not zero and the curl of E is zero for a point charge, because there's no swirl. It is only radially pointed. On the other hand, and I don't know how much of this Tim showed you, if you have a wire carrying current, I, we will get magnetic fields, which will look like, I'll draw them like this, but that kind of wrap around this. Did Tim draw any pictures like this in linear electrical circuits when you talk about solenoids and things? Inductors? No? Okay. So for a magnetic field, we're going to have, well, there's no radial direction here. It's all going around. So we're going to have del dot B, the divergence of B, it should have been dot, is zero, but we're going to have del cross B is not zero. Okay, so just to some extent, that's really the key, and mathematically, that's, at least when you're talking about things that aren't changing in time, that's the main difference between electric and magnetic fields, is exactly the curl and the divergence, the way they behave. Now, this isn't how we're going to introduce it. But we're going to work our way to this point through the course of the semester. But this is going to be the upshot. What that also means, though, is even the simplest possible magnetic field problem involves cross products. And so that's why most high schools don't really even touch them, because it's just by that point in the year, they're just tired. So, all right. Okay, let's go back. I have some practice problems for you guys. So here you go. I want you, oh, hold on. Not the gradient, the divergence. Okay. So I want you to work out the gradient acting on each of these. So the gradient would be del dot F. And they're using ijk instead of x hat, y hat, z hat for their notation. Okay, you can give me a thumbs up when you've got those, or got the first one, I guess. Isaac's got his. Okay, another couple minutes. Okay, I think another couple head nods. All right, so let's work this out. On I call this 1 and 2. So for number 1, the divergence, well, first of all, let me just write out the formula. The divergence on F, that's going to be the partial with respect to X times the X, or acting on the X component only, plus the partial with respect to Y acting on the Y component only, plus the partial with respect to Z acting on the Z component only. Okay, so for the first bit, I only have to take the partial with respect on this. So that's going to give me 2xy plus, and there's no vector left, right? It's a scalar quantity now for the divergence. Now I need the partial with respect to y acting on this. Oh, that's 0. And because there's no y dependence here, it's all z and x stuff, so the partial derivative kills it. And then I need the partial with respect to z acting on this piece, which gives 0. So that's it. Did anyone else, or did anyone have anything different than that? Everybody had that? Yeah? Okay. Let's do 2. so that's going to be, I'm not going to rewrite it. That's going to give me partial with respect to x on this is just going to give me a 3. Partial with respect to y on this is going to give me 2x cubed y over z. And partial with respect to z on this is going to give me minus 1. So we won't leave it like that. Why don't we leave it like that? It's kind of like kissing your cousin, right? We don't do it, you know, maybe it's not quite illegal, but it should be. So let's combine those to write that as 2 plus, actually I would write it as 2 times 1 plus yx cubed over z. Okay, so yes, you should do math correctly, but you also shouldn't kiss your cousin. So remember that. Important lesson in there somewhere. All right. Give me a thumbs up if you had the same results.
So there's no 2 plus, it's just 2 times 1.
I've regrouped it. Oh, the plus 2, I just factored out a common factor of 2. Yep. All right. Everybody has that, I hope. All right, what I'm going to do is I'm going to pull this down and have you guys work out the cross product for the same two vectors. I'll write down the formula, or actually, well, I'll write the formula for you. I'm a jerk, but not that big of a jerk. All right, so the gradient of, or sorry, the curl of f is, just think about doing the determinant. It's going to be x hat, and then you have to do, the partial derivative is in the middle row and the functions, or the vector is in the bottom row. So it's going to be partial y acting on the z component minus partial z acting on the y component. And then the second term in the cross product gives you there's a minus sign there when you do the determinant, y hat, and you're going to get partial x acting on the z component minus partial z acting on the x component. And then the next term in the determinant goes back to a plus sign, and I get z hat. It's going to be partial x f y minus partial y f x. Whew. So now we can crank it out. So on number 1, number 2. All right, it's about as much fun as it looks. X hat, not to work out all this. Partial y on the z component gives nothing, minus partial z on the y component. So that gives me minus, and then I have another minus, and then I get 3z squared. So plus 3z squared for this bit. Minus y hat. And I get partial x on the z component. That's going to give me plus 7 minus partial z on the x component, which gives me 4z plus z hat times the partial x on the y component, wherever the hell that is. There it is. Oh, wrong. Oh, crap. I switched functions. Son of a... I knew I shouldn't have wrote those left those right next to each other. I fouled it up because half the time I was looking at one, half the time I was looking at the other. Ah, crap. All right. Because I'm an idiot, I'll have to do it again. X hat. Try it again. I'll only look up here. All right, partial y on this is going to give me 8y minus, I have partial z on this is going to give me another minus 3z squared. Okay, minus y hat times partial x on the z component is 0. And I get partial x on the z component, and then I get, which is 0, and then I get partial z on the x component, which gives 0. And then I get plus z hat. So I'm going to get partial x on the y component. I've already got 2 minus signs there, so that's just going to be 3 minus, and that's going to be partial y on the x component, which is x squared. Let me just double check this before I move on here. 3y. I'm going to get x on z minus z on x, and then I'm going to get x on y minus y on x. Okay, I think that's right. And then, we should clean it up a little bit and just make this plus. Okay, how'd we do? Everyone get the same thing? Okay. Is there anyone who got something different? All right. I'm kind of losing energy on this. It's just more of the same. You just keep turning the crank. You can tell curls have the most minus signs, and so there's the most potential for going wrong. Divergences are pretty quick. Gradients are in the middle. All right. Okay. So let's go back. All right. So those are curls, divergences, and gradients. So that's how we take derivatives. We also need to be able to integrate. And so remember, we had 1D, 2D, and 3D things. So that means the kind of integrals you do may be different. So examples might include, in 1D, you wouldn't calculate areas or volumes. You would calculate arc lengths. That's the natural thing. That's a natural thing to define in 1D. For areas, it's natural to define, for 2D, it's natural to define areas, and 3D, it's natural to define volumes. We also have vector integrals, so flux and circulation. You guys remember doing those integrals, line integrals and flux integrals in Calc 3? Some people are shaking, yeah? Okay. So those will definitely come up all the time. I'm not sure if I'll quite get that far today, but definitely we will have those. Oh, wrong one. Okay. So there are like general formulas for these things for arbitrary coordinates. But again, we will focus on shapes which are lines, a hoop, so like a circle, or a disk, a 2D disk, or maybe an infinite plane, or if we're doing 3D things, a spherical distribution, or maybe cylindrical, maybe, but we don't do random shapes. Okay, so because of that, it's probably easier if we just kind of go through and list out. I mean, there's a general formula for arc length, but we might as well go ahead and specify and kind of specialize it for the cases that will ever come up for us, right? That way you don't waste time with some, working out some change of coordinates. We basically just have simple combinations anyway. So let's just write those down as they are relevant to us. Okay. All right. Is that all right? So that's kind of the logic of what I want to do next here. And I apologize, my notes are I didn't get them all typed up here, so I may have to handwrite some stuff. It takes a while to type everything. Okay, so there's this general formula for the arc length. Have you seen this formula before? Is that how it looked, or did they write it with? People also sometimes factor out like a dx, and they'll write this as square root of 1 plus dy dx squared times dx. That might be. Is that how they wrote it more? I don't know. So all they're doing is kind of factoring out a differential from the square root. If you write it this way, it kind of makes it clear that what you're really doing is, if you have some curve and you pick 2 points and you want the arc length between them, what you're really doing is, here's the change in x, here's the change in y, and what you're really doing is working out the hypotenuse of the triangle between them. So that's why it looks like a Pythagorean theorem sort of formula. That's where that comes from. Okay. All right. Now, if the path is parallel to the x-axis, so it's like a wire running parallel to the x-axis. So like, here we go. Here's y, and here's x, and here's a wire running parallel to the x-axis. How much is y changing in that case? Not at all. So dy along this curve is just 0, which means this is 0, which means ds is just dx. So ds, which would be just a little tiny bit of line segment, is just dx when it's parallel to the x-axis. Similarly, if it's running vertically, then it's not changing, then dx is 0 on that. So I marked out a little bit of line segment. I would say ds equals dy. Okay, and so if dx is 0, you're just going to say ds is equal to dy. Right? Can you give me a thumbs up if that makes intuitive sense? Some people are saying yes. Yeah. Okay. All right. If you were at some other angle, 45 degrees or something, you'd have to figure that out using trig. Okay. What about circles? So if you have a circle, well, we already know the formula for arc, from high school. We know in general, if I had a wedge with an angle theta, we know the arc length would be S is R times theta, right? So if you went all the way around, you get 2 pi R, where theta has to be in radians. That's important. So if theta is in radians, then, if you went all the way around, you get 2 pi R. If you went halfway, you get pi R. If you went a fourth of the way, you get pi over 2R. Well, no surprise then, if I made it theta differential, ds is going to be r d theta. Now, you can check that. Let's see where that comes from. We'll do this one right here. So let's work out. Remember, x is r cos theta y is r sine theta. And r is constant on a circle. So that means that dx equals, well, r, circle has constant radius, so r is constant. Dx is going to be minus r sine theta d theta, using the chain rule, or yeah, and dy equals r cos theta d theta. So you can evaluate the square root of dx squared plus dy squared, because that's ds, and you get the square root of r, well, the minus sign goes away, so I'm just going to get r squared sine squared theta times d theta squared plus r squared cosine squared theta d theta squared. I can regroup this to write this as the square root of r squared d theta squared times sine squared plus cosine squared. And this just gives 1, so you just get r d theta. So that's one way to motivate that formula, that the arc length for a circle is r d theta. You can get it from the things we saw last class and some arithmetic. Do you guys remember seeing that before? Is that something that she did for you guys?
We use this with triple integrals, right? When we're changing like dx, dy, and d whatever to those.
Well, you would. So this wouldn't be triple. This is just because these are all 1D curves. But there's a version of this, yeah. And you can work out something called a Jacobian, which is this change of variable thing. Yeah. I'm not going to write it out. It's like, to do it in spherical coordinates gets pretty gross, but I'll just write the answers down. All right. It's not, yeah, it's a little bit afield from what we need to do. But we do something, yeah, you can always change variables. Here's the deal. This is important. What is kind of physically relevant or physically true are length, area, and volume. You can choose any coordinates you want. So you can slice it up. It'll still be the same volume. You just slice it different ways. So that means that any set of coordinates must have some way to rewrite the integrals so that you'll calculate the volume to be the same or the area to be the same. Now, the math of how you make those changes of variables it's not that bad, but it's just, again, we only deal with pretty simple shapes, and so it's probably just more efficient to just tell you the answers for those rather than go through all the conversions. Okay. What about areas? Areas. So the area differential is so this is a 2D area in a plane. Okay, so in an XY plane. So what you're basically doing is imagining, you have some, let me draw a picture here. So you got X and you got Y. Imagine some shape, and you're going to calculate its area by adding up little postage stamps, kind of like, like always playing Legos. Okay. Now you can make your postage stamps kind of line up with the X coordinate, X and Y coordinates, in which case you would say, oh, so, and the area of each little postage stamp is area dA, and you'd say, in particular, you'd say the total area is simply the sum of all the little areas, the integral dA. So in Cartesian coordinates, you would use dx times dy because it looks like a little rectangle. In polar coordinates, you kind of have to think about it. What you sort of get, it's almost like a little fan. Okay, so one side of the postage stamp is at fixed radius, so it sweeps out a little arc. Then the next side is at fixed angle, but you change the radius, so it kind of forms a radial line. And then the top bit would be, again, it's at fixed radius, and you sweep out another arc. And so there's a little so this would actually, well, okay, whatever. And then the last one would be of length dr. So what you get is kind of like a trapezoid. Well, in the limit, it looks like a trapezoid. And on one side, you would have, this had size r dr, sorry, r d theta. This would have size dr. This would be size dr. And this would be size r plus dr times d theta. That would be the length of this side of it. And but you'll notice this is like differential squared already. So that basically means this piece goes away. So you'd work out, it looks like a trapezoid, use the formula for the area of the trapezoid, and it's the average of the sides times the width. Anyways, and what you'll find is that to second order in differentials, this is the formula you get for the area. It basically looks like a rectangle. Or sorry, just use the area formula for a trapezoid with these lengths, and you'll get this formula to first order. Okay, so the formula for the area in polar coordinates is r dr d theta. And I'm sure that she showed you that formula. Yeah. If people are confused when we meet face to face, I can try to elaborate on it. All right. Is that okay so far? Let's use those. Oh, there we go. And when you do integrals in higher dimensions, remember you just do the iterated integral. All right, so you do the integrals one right after another. Just take the output of the first one and integrate that answer to get the next one. All right, so what we're going to imagine here is we have a circle of radius r. I'm going to use capital R because, why not? All right. And what I want you to do is calculate the arc length around this circle. Okay, calculate the perimeter of the circle. So, step one, write the problem down. Then then the first thing you really want to do is, what is the arc length differential for this problem? Namely, what coordinates do you want to use for this circle? Do you want to use Cartesian coordinates, or do you want to use polar coordinates? And then two, set up that the arc length equals the integral ds. Okay, who thinks they might have it? Zeke says yes. Billy says yes. All right, so let's go through this. And this is how I will do a lot of these integrals. I will write things down in terms of some sort of general abstract thing, which is guaranteed to be right and is completely useless from an actual calculation point of view. But by doing that, I anchor myself to something I know is right. I know that the arc length is what I get from adding up little baby steps. And then I go through this. So in this case, I'm going to choose polar coordinates. So I want to choose ds equal to r d theta, except that r is, I said I'm going to call it capital R. Just, small town, not much to do. I'll do it that way. And theta, as I go all the way around the circle, runs from 0 to 2 pi. So I would say that the arc length equals the integral ds, which is the integral from 0 to 2 pi of r d theta. R is a constant on the circle, so I can pull that out. And write that as r times the integral d theta from 0 to 2 pi, otherwise known as 2 pi r, the circumference of a circle. How many people were able to do that? Okay. If you weren't able to, tell me where did you feel like you got stuck so I can adjust?
I just didn't pull the constant out.
Oh, okay. So we will go through this process for all sorts of different quantities, charge, current, area, volume, all sorts of things. And you have to be careful. You can pull any constant out, even if it's a vector. If it's constant, you can pull it out. Sometimes you can't. So you got to just kind of know. You got to look at the picture and think about it sometimes. Yeah. I will also tell you this in this course, because we will have lots of R's. R for radius, R for position vector, R for whatever, polar coordinate. What I typically do is I use capital R for fixed things. And I tend to use lowercase r for variables. That's just kind of my own way. Really, it helps me so that when I look at something, I don't, start taking derivatives of something that's constant or start ignoring something that's variable. So if I kind of use capitals a lot of times in the geometry when something is fixed, and when something's like a coordinate value that might vary as I move around, I leave those lowercase. That's what I do. So just to help me. All right. Okay, we're running pretty short on time. All right, let's do 3D shapes here a little bit quick, and then I think that'll be enough to get us started. And then on Tuesday, we will plan to meet in person. And on Tuesday, we're going to actually start doing physics kinds of things. And probably do our first kind of hands-on lab activity. I don't know if we'll quite finish, but we may split it up over a couple of days. Tuesday we'll do that by next, yeah, So then we'll be off and running. All right, 3D volumes or 3D shapes. Actually, you don't have to do, you could also do areas. In particular, you could do surface areas. You could have a surface area in 3D. So in 3D, you could have a ball in 3D, it has a surface area inside it. So if a problem is a 3D problem, you might have to think about area, or you might have to think about volume, and you got to kind of know what's appropriate, right? And we will have cases of both. So all right, hold on here, control, hold on, let me insert it. Good. All right, so here are spherical coordinates. Yeah. Oh shoot, they've got the angles flipped. Remember, I'm calling this angle theta, and they're calling it phi. Sorry. All right. So whatever. All right. Watch the angles. Okay, reverse theta and phi from what we did last time. And I will always do it the other way. That's what happens when you pull stuff off Google. It looked really good when I pulled it up, and then I zoomed in and it's like, oh crap. Okay. So here's the thing. If you have a surface area, dA, on a sphere, it equals r squared sine phi d phi times d theta, where this is the azimuthal angle, and this is the polar angle. Okay, so this is the formula for the area on a sphere. Let's just check that. Does anybody know what the surface area of a sphere is? You remember the formula? 4 pi r squared is the surface area of a sphere. So let's just check that. So I could do the area is the integral dA. Again, that's the kind of trivially true statement, but I usually start the calculation with something like that so that I'm anchored to something I know is true. And then I just start evaluating things. And if this is a sphere of radius r, I'm going to say I'm going to say that radius is constant. So I'm going to write that as the integral of r squared sine phi d theta. This is a double integral because I have two. I'm doing back to back. I have phi written first, so I'm going to integrate phi. Phi runs from 0 to what? The azimuthal angle runs from 0 to what?
90.
180.
180, or
Oh shit, yeah.
pi. And then theta runs from 0 to 2 pi. Okay, so first do the interior one. Well, r is a constant because it's a sphere. So you can pull that out. So you get r squared. Integral 0 to pi. Integral 0 to pi. Sine phi d theta. Whew. Okay, what is the integral of sine? Careful with minus signs.
Negative cosine.
Minus cosine. So this part gives me minus cosine of phi evaluated between 0 and pi. That's on the inside. And that is actually equal to negative 1. That's plus 1. Minus 1. It's 2. And you have to integrate that from 0 to 2 pi. This stuff came from up front. And sure enough, I get 2. The theta integral gives me another factor of 2 pi, so that's a total of 4 pi and r squared, which is the right answer. Okay. We will see that when we calculate flux integrals we'll have the flux of a vector field out of a surface, and we'll need that. I'm going to go ahead and just tell you, for the volume integrals, I can think of a volume, if I've got a region in 3D, you can kind of break it up into little sugar cubes and then find the total volume by adding up the effect of each little sugar cube. So you can say it's the integral dV. In Cartesian coordinates, dV is just going to be dx, dy, dz. It's like the volume of a cube. If you're in spherical coordinates, what you actually have to do is you get like this. It's not a cube anymore. It's kind of the analog of that in spherical coordinates is kind of like a blob of jello that kind of fans outwards. It diverges a little bit on the outside. And when you calculate the volume of that little blob of jello in spherical coordinates, you would say it's this. And you would say it's equal to r squared. Now r, because I'm integrating over volume, r is a variable, not fixed. So I'm going to use lowercase. R squared sine phi. This is the same r squared sine phi that we had up above times dr d theta d phi. All 3 differentials. You guys remember seeing that before? Stephanie probably would have said rho squared sine phi d rho, but I'm going to say rho to mean charge density. Okay, well, I was hoping to do an example with volume integrals, but we'll have lots more practice this semester, so don't worry about that. Before I let you go, how do you feel? Does this stuff seem sort of familiar, or does it all seem like a foreign language? Sapan says yes.
Similar, but slightly different.
Okay. I'm sure the way I write things is different. And yeah, that'll take some getting used to. Okay. All right. I will let you guys go. Remember, you have a sapling due tomorrow. It's on cross products and dot products. So hopefully that's pretty easy.
What time does it due?
Sapan, you were supposed to finish it
I haven't
early. I mean, do you have other classes?
Yeah, but I haven't enrolled in the course.
Okay.
So
Okay.
I don't know. I don't know anything about that.
Okay. It's due at midnight. So I think how many questions are there? Do you remember?
Like 10.
10, something like that. So dot product and cross products of vectors is really what it was. Okay. That's all for today. Next time we'll start doing some real physics, not just math review. All right, let you guys go.